All right, we're going to move on to related rates. Related rates is one of the most useful applications of the derivative. It's an application that involves implicit derivatives, and so we do it after implicit derivatives for that reason. It's all implicit. The key here is it looks really complicated. If you turn over to the back of your notes, there's this list of 11 things you have to consider. I want you to know that I am going to do my best to simplify this list of 11 things into a manageable process and show you how to do related rates. Here's the idea. Things move. Yeah? Things move. Anybody seen a lighthouse? Lighthouse? Let's say there's a lighthouse on an island and the spotlight from the lighthouse, you know, it spins. They do spin, right? Okay, so the rotation on the light of a lighthouse has a constant rate of change typically, right? It doesn't go fast and then go slow and go fast and go slow. If that rotation on the light is held constant and there's a shoreline a mile away, that's a long ways. Maybe there's a shoreline a couple hundred feet away. It's not wide enough for a boat to get through. Anyway, there's a shoreline, and you can actually, knowing the rate at which the lighthouse rotates, you can calculate how fast it's going to move along the shoreline. Kind of cool. That's a related rates problem. Example 1, there's a balloon. If you're standing, I don't know when you'd ever find yourself in this situation, but can you imagine how cool it would be if you did? You're standing here, a balloon just happens to be 150 feet away from you, and you can see it, and you want to measure the distance between you and the balloon. Well, before the balloon is released, you're 150 feet from it, right? If we know how fast the balloon rises, we can use related rates to calculate how fast the distance between you and the balloon is changing. You agree that that distance would change, right? If the balloon is moving 8 feet per second, will it be moving away from you at 8 feet per second? No, it's moving away from the ground at 8 feet per second, and the rate at which it's moving away from you is a little bit different. So related rate problems involve something moves, and it can allow us to calculate how fast something else moves. Concept okay? Let's dig into it a little bit. You are going to need to know some things from geometry. Not a lot of things for geometry. AP will often give you, if they're dealing with a volume of a sphere, they're not really expecting you to remember that the volume of a sphere is 4/3 pi r cubed. They're not necessarily asking you to remember that the surface area of a cube is 4 pi r squared. I think those are right. I sure hope those are right. That's how I remember them. They're not expecting you to remember those things, but they might ask you to remember things like Pythagorean theorem, trig ratios. All those things are going to come into play over the next couple of days. So let's go through example 1, and I'll kind of set up how I think through these things, and you can bear with me and make some arguments with me as we go. So at least for the setup portion, we want to break this down into what we want to find based on what we're given and when that occurs. So based on reading this problem, I assume during my rant over the last 2 minutes that you read this problem. Did you? If you didn't, take 20 seconds to read it now. Okay? And I actually, from my perspective, I like to know what we're given first. And typically, this is a given rate. What rate are we given? What rate do we know the number for? We have the rate of change of the balloon. We have 8 feet per second. Okay? We know that's going to change, so we need a variable for the height of the balloon. I like to use variables that make sense, so I'm going to call that h because it's the height of the balloon. Okay? So now, if the height changes, feet is a measure of height, so change in height. Seconds is a measure of, what does seconds measure? Time. So this value is dh dt. We'll get to that derivative piece in a minute. But you need to know that that's the change in height over the change in time. Now, if you had called this distance over here x, it would be dx dt. But we called it h, so we're going to use dh dt. Right? What else do we know? Let's do what we're trying to find. I know what we do given first. What are we trying to find? Here's the question mark. How fast, distance, balloon to observer. We need a variable for distance from the balloon to the observer. This is what we're trying to find. We're trying to find the rate of change of the hypotenuse. Okay? I'm going to call this, and fifth hour got mad at me, but I'm going to call that D. That is the actual distance between the balloon and the observer. We could call it B. Doesn't really matter. I'm going to call it D because it represents the distance that we're trying to find. Okay? So if the hypotenuse of the triangle is D and that changes, we have to use the variable, and that is what we are trying to find. We're trying to find the rate of change of that balloon to the observer. We're trying to find dd dt. And it's going to be in what units? Feet per second. Okay? If we have two things that change, most often you're going to have one thing that stays the same. What's the constant in this problem? That is constant. Okay, now on your original drawing, label constants as constants and label things that change as variables. Okay, now we are given a condition, but I don't want you to put that given condition on the original triangle. Because if you put the given condition again, if you didn't do h here and you did 50 here, there would be no change. Do you understand that idea? If this was 150 and this was 50, this would always be the square root of 25,000. Right? I'm working ahead of you. You're wondering where I came up with that. We'll come back to it in a minute. I already did this problem once today, so that's why I remember that strange, obscure fact. Okay? The when is the given condition. That is, when is this happening? That is when h equals 50. And we're going to consider this situation later. Okay? Once you've identified what you're given, what rate you're given, what rate you want to find, we're going to use our picture and what we know about geometry to make a simple equation that relates the variables. Related rates. Relates the variables. Don't worry about derivatives at this point. We're not worried about dHdt or ddt at this point. All we care about are h, d, and 150. Tell me something that helps. Whose theorem? Pythagoras. It's the Pythagorean theorem says that h squared plus 150 squared equals d squared. Now you can say x squared plus y squared equals z, or a squared plus b squared equals c squared. That's how you learned it, isn't it? You could write a squared plus b squared equals c squared because that's common and everybody knows that. But I don't want you to leave it in terms of those variables. I want you to use the variables that are given to you. Does that make sense? Okay. Once you have the equation, you are now going to find a derivative. Okay. What variable are your rates given with respect to? What variable are your rates with respect to? Time. Do I have time in here yet? No time here yet, right? But I'm going to find the derivative of this equation with respect to time. Watch how cool this works. I'm going to take both sides, and I'm going to differentiate with respect to time. Now, this is an implicit derivative, and you know how when we did implicit derivatives in the beginning, you kind of wondered, well, when do I need to do I dx and when do I not? You always, in these problems, are going to need the variable with respect to time. So when we differentiate, it looks like this. H squared is a nice power rule problem. It becomes 2h dH dt. Why dH dt? Because I'm differentiating with respect to a variable that's not the one I've got in my expression. H and t are not the same, so I need a dH dt. Cool? What's the derivative of 150 squared? 0. Why? Because it's a constant. 150 is a constant. We're thankful for constants. They have nice derivatives. Derivative of d squared? 2d d dt. D dt. Okay, the derivative with respect to time. Good so far. So, number 1, setup, variables. Number 2, simple equation that relates the variables. Number 3, differentiate with respect to time. Okay? Now, I like at this point to consider which one of these, I'm going to go back up to my information from the beginning, which one of these do I want to solve for? dt, this is the one I want. And the key to algebra is if I want one of them, I need to have or be given or be able to find all of the others. So what are we given? We know this, right? 8? What's the answer for that? The HDT is 8. So 8's going to go in here. We know H. What's H? 50. I'm going to substitute in a minute. I'm just making notes right now. This isn't actually how I would do it. But I'm kind of making notes on what goes in where. What else do I need if I'm going to solve for ddt? I need D. And I'm going to use the given condition. I'm going to use the 50. At that instant, I'm going to use the 50 to find D. Ready for that? I'm going to go off to the side here. This is under the given circumstances that this is 150 and this is 50, right? Now, I can only do this 50 after I've done the derivative, because we talked about it before. If I let this be 50 and this be 150, there's no change, okay? So under the given circumstances, that's true, and this is D. So D squared is equal to 50 squared plus 150 squared, Pythagorean theorem again. D squared is equal to 5 squared is 25, 2 zeros because there's zeros. 15 squared is 225, 2 zeros because it's squared. Good? So 22,500 plus 2,500 is 25,000. I'm not some sort of savant. I did this problem already. That's 25,000 underneath the square root. I'm not going to go any further than that at this point. Okay? So at this point, we're going to substitute everything in. So I'm going to say, I'm going to just go down here. 2 times 50 times 8 plus 0. I'm not going to write the plus 0, guys. I hope you're okay with that. 2 times 50 times 8 equals 2 times the square root of 25,000 times dt. How do I solve for dt? Divide. So this is 2 times 50 is 100 times 8. That's 800, right? So dt is equal to 800 over 2 square roots of 25,000, aka 400 over the square root of 25,000. Do you need to go here? I wouldn't. I'd leave it right there. Okay, they're often going to ask you to include units. Go back to your given information and tell me what units should be on this answer. Feet per second. If you have a calculator, you can evaluate it. If it's a multiple choice question, you're going to need to evaluate it with a calculator. But on a free response question, you don't need to simplify that answer. Okay, good so far. What's the process? You get the setup. You find out what you're given, you find out what you want to find, and you identify the variables that are important. Make a simple equation that relates them. It's a geometry problem. It's either going to be a tan problem or a sine problem or a cos problem or a Pythagorean theorem problem or a volume of a sphere problem. Find the derivative with respect to time, put in what you're given and what you can find out, and solve for the variable that you're trying to solve for. Good so far. Okay, let's do at least one more. We take just a moment, and will you identify what you're given, what you want to find, and the when? All right, where are we at? What did you say was given? What number and what notation? 8 cubic feet per minute. What is that a measure of? It's a rate because there's a measurement over a measurement. dV dt. Because cubic feet is a measurement of volume. Units are going to help you here. It gives you cubic feet. That is definitely a volume. Square feet would be an area. Feet would be a length measurement, so that is going to be dv dt. All right? We're asked to find how fast the water level is rising. The water level is represented by what in this picture? H, R, or V? Here's what I'm going to do. Here's what I'm going to do that I think helps. I'm going to draw some sort of representative water level in here. I realize that 12 and 6 are given, but the height of the water is not always 12. You with me on this? Because it's going to fill and that height is going to change. So you can't use 12 for the height. So I'm going to call this H, and I'm going to call this R, R being that distance right there. All right? So I'm going to find how fast the water level is rising, which is dH dt based on my picture. And when am I going to do that? I'm going to do that when h equals 4 feet. Okay? What variables are most important in this problem now? Two of them, really important. V and h. R is a variable that's in play here. We're going to do something in a minute to get rid of it because we don't want it. Okay? Give me a simple equation based on the shape of the object that gives us the variables that are important. What have you got? I need a V, I need an R, and I need an H. That's the volume of a cone, right? Cone or pyramid? Well, not really a circular pyramid, that would be. Okay? 1/3 base area times the height. That's the volume of a circular cone. Good? Okay, which variables did we say we really care about? V and H. If we care about V and H, we should get rid of the R, and here's why. Remember that whole implicit derivative process with respect to T? The more variables I have, the more rates I'm going to have. I would have a big nasty product rule problem with a dV, a dr, and a dH. I cannot deal with 3 rates because I have one and I want one. What am I going to do with the third one? Make it up? I wouldn't do that. Okay? So we need to do something to get rid of the R. And what we're going to do is we're going to use the 12 and the 6. This is 12. And this is 6. Do you see it? Don't say it out loud yet, but do you see it? There's a really important geometry concept here that involves this and this. The water has to be inside the cone, so the water will conform to the shape and the measurements of the cone. Agree? We're not going to expand the cone. What is the relationship between radius and height for any cone that I do here? Or not any cone, but any level of water. The radius will always be what? Half the height. Why is that true? Starts with an S. So they're similar triangles. We okay there? I don't want to go through the proof of similar triangles. You're just going to have to believe it for now. Okay? Ask your geometry teacher. Okay? So what am I going to do? I'm going to take 1/2 h and I'm going to put it in here for r. So now I'm going to use this new equation that is way cooler than the first one. 1/3 pi 1/2 h squared times h. Why is this cooler? Because it's only got the variables in it that I care about. Now, does the radius change? Yeah, there's a dr dt, but I'm not asking for it here. Okay? Another thing that's really important, the simpler you can make your original equation, the easier it is going to be to find the derivative. So will you go ahead and simplify that for me? What'd you write? There's going to be a pi, and there's going to be an h cubed. What goes in front? 1/12. Where does 1/12 come from? 1/3 times 1/2 times 1/2. There's a square on the 1/2. What's that? I would simplify the equation, because if you don't simplify the equation, you've got a product here. You at a very minimum need to simplify the h squared with the h. Okay, I think it's a really nice thing to have that coefficient there simplified as possible. Okay, but you need to simplify the h cubed, otherwise you're dealing with a product rule, and you don't really want to do that. Or maybe you do. Wouldn't be wrong, just be a lot more work than you need to do. Okay? Volume is as simple as possible. What are we going to do next? Differentiate with respect to time. That both sides of that thing. dv dt is equal to a nice little power rule here. I can do it this way too, though, guys. 1/12 pi is a coefficient. I could just write that as pi over 12 times 3h squared dh dt. Does that help? Really just dealing with the h cubed rather than dealing with the coefficient, because the coefficient is a constant. It's just a scalar multiple of the derivative. Okay? Again, once I've done the derivative, I like to double check. Am I trying to find dv dt or dh dt? dh dt, this is what I want. And I like to do a mental check. Do I know this one? Do I know dv dt? Yep, they gave it to me. Do I know h? Yep, they gave it to me. We're in good shape for solving now. Okay? So dv dt, was that 8 again? I feel like that was 8, 2 problems in a row. So this is 8 equals pi over 12 times 3h squared dh dt. Solve for dh dt. Let's see here. This is pi over 12. 4 squared is 16. 16 times 3 is 48, right? Times 48 times dh dt. I'm going to simplify the pi, 48 pi over 12 to just 4 pi, right? So that's 8 equals 4 pi dh dt. So dh dt is equal to 8 divided by 4 pi. If you want to simplify, you can. It's 2 divided by pi, and that is in what units? Go back up to the top. Feet per minute. Cubic feet per minute or feet per minute? It's feet per minute. Why is it not cubic? Because we're measuring the change in the height of the water, not the volume of the water. Okay. We could go through dimensional analysis and show you that this all works with the units appropriate, but I don't really want to do that today. Quick question. Sorry? Scroll up. Okay. What I'd like you to do, I hope you have a half pink sheet with assignments. This is what we're doing the next couple of nights. Will you do day 1? The page numbers I don't think are right. I don't think the page numbers have been right most of the chapter. But will you go to section 3.11 in your textbook and do the day 1 problems? To give it your best effort. We didn't get through all of them. Tomorrow we might do a sphere problem, and we'll definitely do like a rotation problem like a lighthouse. And maybe we'll do a ladder problem. Did you know that if you have a ladder up against the wall and you move the bottom of the ladder away from the wall, that the height of the ladder doesn't change at the same rate as the base of the ladder? You knew that, right? Well, we're going to do it tomorrow, just for fun, because of course you want to do ladder problems.